Electron configurations are a convenient text-based way to represent the information that we get from an orbital filling diagram. So I have an orbital filling diagram that's been filled out for selenium. This is the ground state of a selenium atom. And I want to talk about how we can represent those in electron configurations. We have two ways that we do that. One is a complete electron configuration, and the other is a condensed electron configuration. The basic concept here is you start with the lowest energy orbital, you list the name of the orbital, and then indicate how many electrons are in it using a superscript. So for the 1s orbital, if we look down here, there are 2 electrons in the 1s orbital. So we would write it like this, and we would say 1s2. When we look up one higher at the 2s, there are 2 electrons in that orbital. The 2p is the next highest energy. There are 6 electrons in the 2p orbital. And then 3s2, 3p6, 4s2, and now the 3d10. So in all of the 3d orbitals, there's a total of 10 electrons. And then we come back to 4p. Now, the 4p orbital can hold 6 electrons, but in this orbital filling diagram, there are only 4. So this is a 4p4. Okay. This is a lot of stuff to write out, and what we're really interested in are these valence electrons. So in this case, here and here. Okay. And so when we write these condensed electron configurations, what we can do is we can look at these sort of core electrons, these early electrons, and we can summarize them. And what we do is we take a noble gas, in this case it's going to be argon, and we put it in square brackets. What that argon in the square brackets represents here is all of the electrons in the ground state of argon. Now, all of our noble gases have complete subshells. So this would be helium. It is completed or filled the 1s orbit or the n equals 1 orbitals. All of these electrons collectively are neon. Okay, when we go from 2 heliums, we add another 8, we end up with n equals, or 10 electrons. If you look at a periodic table, Z equals 10 is neon. Okay, we've completely filled the n equals 2. That's why neon's particularly stable. And when we go to fill n equals 3, going from 10 to 18, that's argon. Okay, so that's what those square brackets represent. You go to the previous noble gas, put that noble gas in square brackets. And then you list your orbitals. And it's a little strange with these transition metals in this example I picked. We're going to place the 3d10 first. Then 4s2, 4p4. If the d orbitals were not full, I would not move them to the front. They would stay at the end. Given they're full, they move to the front. And that's the condensed electron configuration of selenium. Now I want you to notice something as we look at different elements in group 6A. So we had argon, 3D, 10, 4s2, 4p4. If you were to do this same process for sulfur, you would have neon as the previous noble gas, and then you would have 3s2, 3p4. And if you did it with oxygen, helium would be the previous noble gas, and you'd have 2s2, 2p4. Now recall that the periodic table was organized this way because all of the elements in that column show similar chemical behavior. And now we have an explanation as to why. They all show similar chemical behavior because they have similar configurations of their valence electrons. While they're further away from the nucleus, which affects some things like ionization energies, we have the same number of those valence electrons. There's another item I want you to note, is in each case, the number of valence electrons is 6. And that's why this column in the periodic table is labeled 6a. This is a very convenient and easy way to identify how many valence electrons there are in an atom without doing this whole orbital filling diagram and electron configuration process. If we come back here, the highest principal quantum number were valence electrons. All of the others are core. Now in this case, the 3d10 is a set of core electrons because it's full. In the example we did last time with chromium, the d orbital was not full and it counted as the valence electrons. Okay, and from this you can sort of predict that tellurium will be krypton, 4d10, then 5s2, 5p4. Okay, and if we went below that, it would be the next noble gas, which I believe is xenon, 5d10, and it'd be a little more complex down there because we're getting into f orbitals. Okay, so last bit on this is some observations about what happens in this periodic table. And I'm going to go ahead and divide it into regions. I'm going to label this the S block. These elements in the S block have their most recently added electrons, their highest energy electrons in an s orbital. Okay, so the group 1a has a single upspin electron in an s orbital. In hydrogen, that would be 1s. In lithium, it's 2s. In sodium, it's 3s. And potassium, it's 4s, etc. Beryllium, magnesium, calcium have 2 electrons in the s orbital. So their s orbitals are full. Beryllium would be in 2s, magnesium's in 3s, calcium's in 4s. Helium's a little weird, it's over here. That has 1s2, so 2 electrons in the 1s orbital. Okay, the next block I want to highlight is here. And I'm going to label this as the p block. Well, we should extend it over to include the noble gases, sorry. The p block are elements where the most recently added electrons, the highest energy electrons, are in p orbitals. Okay, so boron has 1 electron in the 2p orbital, carbon has 2 electrons in the 2p orbital, etc. The noble gases are particularly stable because now all of the n equals 2 orbitals are full. This region here is the d block. And the d block are elements where you're filling the d orbitals. I want you to notice something. We have 2 columns in the s block. Okay, 2 electrons can go in that s orbital. We have 6 columns in the p block. That's 2 electrons. 1, 2, 3. I shouldn't draw it that way, sorry. 1, 2, 3, 4, 5, 6. 6 electrons in 3 orbitals. The d block has 10. 2 electrons, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and you can guess these down here we call the f block, and there are 14. So 7 orbitals, each with 2 is 14. Now you can use this sort of observation of how the periodic table is set up to very quickly figure out electron configurations and where those valence electron configurations are. So if I'm doing iron, I would do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 1, 2, 3, 4, 5, 6, so 3d6. That would be a way that you can use this. I think it's also very satisfying in the sense that understanding these orbital fill orders and the number of electrons that are allowed in each orbital makes the shape of this periodic table make a lot more sense, and why you have this sort of weird cutout shape and things of that nature. So I find it very satisfying that we're starting to pull together and understand why some things are happening. But it's important that you note that we have similar chemistry in a group because we have similar configurations of the valence electrons.